Hi, in this video, we're going to take a look at log ratio transformations for use with compositional data. Specifically, we're going to be interested in geostatistics. Now, we're not going to invoke any geostatistics here, but we are going to talk about the log transformations so that later down the road, we can use these while we're doing our geostatistics. All right. So the log ratio transforms. All right, so the problem with compositional data that come from the fact that they only carry relative information. Remember that if I'm talking about composition data, all of my values are non-negative, 0 or positive, and they add up to a constant, typically 1, 100 for percentages, or maybe like a million parts per million, something like that. And so all of our information is relative to each other, to when I want to look at one data field, that's really the amount relative to the other data fields in my sample. So any relevant quantity must be expressed as a ratio of the variables to be considered. And so this very naturally, by the composition aspect, just leads us to ratios of our measurements. Now, frequently in mathematics, whenever we are dealing with numbers, it ends up that I'm not really so interested in the actual value. I'm more interested in the magnitude. And in that situation, logarithms are the way to go. So what we're going to do, we're going to start using log ratios instead of just a straight composition data to get a mathematically better point of view. Now, it's a little bit harder to interpret. Composition data is definitely easier to go. If it sums up to 1, the value gives me the fraction of the observation. But logarithms have a lot of nice properties, right? If you go back to college algebra, we know that the ratio inside a logarithm is the same as subtraction of the two logs of the numerator minus the denominator logarithms. And so there's going to be a lot of good reasons why we would want to end up using the log of the ratios. Remember that logarithms can, approximately speaking, just approximately, the logarithms convert a number to the magnitude. To see this, you can go and take scientific notation of a number, take the base 10 logarithm of it, and you'll see that what you're going to get is the exponent plus a decimal that's less than 1. And so this way we get that exponent gives us the magnitude of the number instead of the actual precise value. And frequently, in a lot of situations, that's actually easier to work with from a math point of view, even if it's harder to interpret for humans. All right, so rather than working with raw data, we can use log ratios of our variables after a transformation. And the ones that we're going to talk about here, first is going to be the pairwise log ratio transformation, the additive log ratio transformation, the centered log ratio transformation, and then the isometric log ratio transformation is going to be the last one we talk about. Now, when I'm using the compositions package, here are the names of the functions right here. And it's very aptly named. All right, now something that is important, when we run our analysis on composition data, it's important that the results not depend on which transformation was actually applied. All right, so if I get different results with different transformations, then I have contradictory information, and I probably shouldn't trust my results anyway. That's frequently going to be like a small sample situation or very weak signal within the data. And so if I get different results for different transformations, I probably can't trust it. And that's a good indication to back off and reevaluate the situation. And so the transformations that satisfy the invariance are called affine equivalent transformations. All right, so let's talk about pairwise log ratio transform. Well, just like the name indicates, pairwise, we're going to take all the pairwise combinations of the observations within one composition. And so I'm going to have, for one composition, I'm going to have the ratio of measurement 1 with measurement 2, measurement 1 with measurement 3, measurement 1 with measurement 4, and so on. And then I'll do this also with measurement 2, measurement 1, measurement 2 with measurement 2, measurement 2 with measurement 3, so on until I get all D by D combinations. And so we're going to represent this using a matrix very naturally. So rows will correspond to the numerator in the log ratio, and columns will correspond to the denominators in the log ratio. This is how the textbook presents it. Oh, I forgot to tell you where the textbook is. And so this is Geostatistics for Compositional Data with R. Here are the authors' names. University of Central Florida students can download the ebook for free. Here's the GM Geostats GitHub page, and here's one of the authors' professional web pages if you want to dig in. So let's get back to where we were. All right, so the textbook sets it up so that rows correspond to the numerator in the log ratio, and columns correspond to the denominator. All right, and now you'll notice that here I've got Z1 over Z1, I've got Z2 over Z2, following the trend all the way down to ZD over ZD. Well, all these ratios on the inside are 1, log of 1 is 0. So I have 0 on the diagonal of this matrix. All right, so now something to realize is that this matrix is skew symmetric. All right, so remember that if I have if I have a negative sign and I multiply a logarithm, that's equivalent to removing the negative sign and taking the reciprocal of the inside. And so because of that, it works out that the upper triangle portion is equal to the lower triangle or entry times -1. And so this entry here is equal to -1 times this entry here. This entry here is equal to -1 times this entry. This entry is equal to -1 times this entry. All right. And so what this does for us, if my composition has a lot of observations in it, I can reduce the number of things I have stored. And so if I know the upper triangle, I know the lower triangle automatically for free on this matrix. The diagonal is 0. So all I have to do to store the objects, to store the measurements, is get just like the upper triangle or the lower triangle. Typically we do upper triangle. All right. And so now if I want to compute this, so here I can take the compositions from the Win-Darling data set that's in a previous video that we talked about this, and I can go through and I can take the composition. And when I do this, you can see that I have, a combination of values. So it's giving me the ratio of these all the way across. And you'll notice that here I have PFE, and I'm not seeing FEP, right? If I look across, double checking myself before I say anything further, scrolling through, you'll notice that there's PFE. I don't see an FEP in the column names because I don't need it. It's going to be the negative of it. So I just need to have the value once. All right, now there is an inverse function for this using the generalized inverse matrix. So I'm going to talk about the matrix presentation of the formula in a moment, but there is an invertible function using generalized inverse on the transformation matrix. And so here I take the log transformed or pairwise log transformed data. Then I'm going to apply the inverse to it. And I want to show you that you get the same value. So here, you'll notice I get the same value here. I get this value is the same value here. This value is the same value here. And I can keep on going through and double checking. Now, there may not be exactly the same because of machine accuracy rounding off errors, but they're going to be really close up to rounding. And now something that to be mindful of is that you'll notice that I lost the column names when I did this. And so that's something just to be aware of. If you're using this, you're going to need to manually assign the column names afterwards. Now, the next one to talk about is the additive log ratio transformation. All right, so previously in pairwise, we took every possible combination. Well, what we're going to do here, we're going to choose one of our fields in our composition to be our baseline reference level. And so what we're going to do is all the other ones, we're going to go through and we're going to take that log ratio, but we're only going to limit it to the log ratio where the baseline level is in the denominator. And so you'll notice that if I have D levels, I have D minus 1 entries in this vector. And every single time in the ratio, I have the reference level in the bottom. I have the non-reference level, the one that we're actually interested in for the entry, in the numerator. All right. And so this is the additive log ratio transformation. So we're just restricting ourselves to the non-zero part of a row in that pairwise matrix. And we're choosing to, on this presentation, this choice, we're using that last column as our reference level. All right. And so here is how we get the additive log ratio transformation using compositions function. And once again, we have an inverse function to work with. And so here is the inverse function. Once again, it uses generalized inverse for this. And when I do that, I will see that I get the same values. So here, 0.633, 0.633. Let's see, we've got 0.00083, 0.0083, and you can go through and check that up to rounding, they're the same thing. Now, this inverse is called the adaptive generalized logarithmic transform. And so here's just the equation presentation of it. But it has a special name, an additive generalized logistic transform. All right, so now the next one to talk about is the centered log ratio transformation. Okay, so this does it a little bit different. So instead of having a reference level, I want to invoke the entire composition into this. And so what I'm going to do, I'm going to take the geometric mean of my composition, and I'm going to put that in the denominator instead. So this way, I'm invoking the entire vector into the log ratio transformation. All right, and so here I'm taking the product of the entire composition. I'm taking the dth root. So this is the geometric mean of my composition. Then I divide each entry by the geometric mean, and then take the logarithm. And that is our centered log ratio transformation. All right, well, just like before, we're going to go through, we're going to use the compositions function to perform the centered log ratio transformation. And here we can see the results. And once again, we have an inverse function to do the inverse of the operation. Okay, so let's take a look at what that looks like and compare that to the original data. And once again, I see the same values up to machine accuracy. Check that out. And now here is just an expression, mathematical expression of that inverse. Now, the next one we want to talk about is the isometric log ratio transformation. And so this is often used in non-geostatistical composition data analysis due to its theoretical properties. So this has some nice theoretical properties that we'll get to in future videos. And so in the compositions package, it's ILR for isometric log ratio transformation. And once again, I have an inverse function. All right. And so I can go through and execute very nicely. And I'll end up getting the same exact values once again. Now, let's talk about a general expression for these transformations. Well, what we can do is we can actually use a matrix to express this. So we're going to take the log of my composition. Now, when I say log of composition, this is going to be the vector of logarithms of the individual entries. And then I'm going to hit it on the left with a particular matrix. So the matrix is going to have D columns and 0 row sums. And that's important. And so it's going to work out that this will be our generalized inverse formula right here. And we're going to be invoking the generalized inverse of that matrix that we are hitting our log vector with in the first place. And so the psi matrix, the one that's doing the transformation for additive log ratio, is going to be the d minus 1 identity matrix with a column of negative ones appended on the right. Now, our inverse is going to be the identity matrix appended with 0 on the right, and then 1 over d times the identity matrix as d minus 1 d dimensions. And so it's all going to be all one. It's the all one matrix of dimensions d minus 1 d. Now, for the centered log ratio transformation, something that's neat is that the matrix and its inverse are the same. And so it's going to be identity minus the all ones times 1 over d matrix. And for the isometric log transform, now here it's a little bit more flexible depending on which version we're actually invoking. It's going to have we're going to have d minus 1 by d, and we're going to have psi equals phi. So the transformation matrix is going to equal its inverse. All right, now the last part of this section is to take a look at the canonical basis of the centralized log ratio transformation plane used in the other transformations. So we can compute the basis of a centered log ratio transformation plane, and we will use this when we do the isometric log ratio transformation or the planar transform of a composition. We haven't talked about this one yet, but still true, still applies. And so here you can see that if I drop in my composition, I can get the canonical basis going real easily. And you'll notice that these add up to 0. Here, that adds up to 0. If I add all these up, it's going to add up to 0. And you can see how things are going, that each column it adds up to 0. And in this particular case, we can see that the only time I have a positive value is in the subdiagonal. Subdiagonal are always, so that's one down from the diagonal is a subdiagonal. And everything above is a negative value, equal amount to get it so it adds up to 0 in the column sum. All right, so all right, next time we're going to talk about the composition geometry of the simplex. We're going to get a little bit deeper into the state space of our sampling space when we talk about compositions. Probably going to be a short video, but it's going to be interesting. It's going to be juicy. There's some stuff I'm going to go over that you probably haven't seen more than likely in data science, and hopefully it'll like really strike hit a chord with you. Well, that's all I've got for you. Life is short. Do math.